Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syamil Bizamri and my college number is 2021 463 467 344, and with my friends we'll present and talk about the subtopic that we choose, which is the quantifiers.
So, what is quantifiers? Quantifiers is an operator that specifies how many individuals in the domain of discourse satisfy an open sentence. What is open sentence? Open sentence, a declarative sentence that contains at least one variable. Next one is quantification. Quantification is an open sentence can be converted into a statement. The last one is quantified statement. By adding some specific phrases will produce a statement. There is two types of quantifiers. First is universal quantifiers. Second is existential quantifiers. Under these quantifiers, we will learn about the quantifiers with one variable, two variable, and lastly the quantifiers with basic connectives.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Mahdi bin Ahmad. My metric number is 2021 882626. I will tell you about one of the quantifiers from this topic, from this quantifiers topic, which is universal quantifiers. The definition of the universal quantifiers by mathematicology is a universal quantification is a type of quantifier, a logical constant which is interpreted as given any or for all. It expresses that a predicate can be satisfied by every member of a domain of discourse. In other words, it is the predication of a property or relation to every member of the domain. It asserts that a predicate within the scope of a universal quantifier is true of every value of a predicate variable. The universal quantifications of Px is the statement that can be called as Px is true for all values of x in the domain. The notation for universal quantifier is like a backward symbol, a backward symbol and x Px, which mean as for all x Px, and or for can be called as for every x Px. So before we continue to example, I will tell you first about the domain or domain discourse. The definition of domain or domain discourse. A domain specifies the possible values of the variable under consideration. For example, let Px is the statement x plus 1 greater than x, and let us assume that the domain is for set of all positive integers. So we need to use only positive integers. We can pick any numbers that is positive. From this example, I pick 1 as example, and the result is 1 plus 1 is greater than 1, which is true. And I take 2 for the next example, and the result is 2 plus 1 is greater than 2, which is also true. From the example, universal x Px is true under the domain of positive integers. For universal quantifier, it is very important to specify the domain of discourse, because without it, universal quantification of a statement cannot be defined. So we need to know the domain first. So that's all from me. Let's move on to the next topic.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Salman Farsi bin Abdul Aziz. Metric number 2021452888. So, you already heard from the Mr. Mahathir about the universal quantifier. Now, let me explain to you about another quantifier, which is existential quantifier. So, existential quantifier is a type of quantifier. It's a logical constant which is interpreted as there exists, there is at least one, or for some. Existential quantification is distinct from universal quantification, which is for all, which assert that the property or relation holds for all members of the domain. Some sources use the term existentialization to refer to existential quantification. In another word, the existential quantifier is there is need to be at least one of the value that is true in the given domain to be considered as existential quantifier. If there is no true value in the domain, then the existential quantifier is false. So you already know a little bit about the definition of the existential quantifier. Now we will look at the symbol representing the existential quantifier. So the symbol is a capital letter of E, which is sideways, as you can see in the slide. If this quantifier is used in the sentence, it will use a certain phrase like there is an x such that bx, or at least one such that x bx, or for some x that bx. Now I already give you a big picture about this existential quantifier. For giving you a clearer picture for this quantifier, I will explain to you with the example. So let us look at the example. So example is let ex be x with the power of 4 is less than x with the power of 2 in the domain of all real number R. What is the truth value of this existential quantifier? So first of all, let's look at the domain. The domain is all real number. Real number is any number that can be integer, positive, negative integer, zero, and also the and also fraction. So we will substitute the value of x with the number of -1, 0, and 1/2. This is for the solution. So first of all, we will use the s is equal to -1, and as we can see in the slide, we will get 1 is less than 1, and of course this is false. And then we will use x is equal to 0. In this formula we will get 0 is less than 0. Again, this is also false. Next, we will use the x value as 1/2, and this time we will get 1/16 is less than 1/4, which is true. So yeah, again, I have talked before, unlike universal quantifier where all in the all the value in the domain need to be true. Uh, need to be true. But for this execution quantifier, even there is just uh, one value that is true in the domain, then the the true value of the execution quantifier is true. Thus, the existential quantifier for x power of 4 less than x power of 2 is true. So that's all for the existential quantifier from me.
Hi, Assalamualaikum. My name is Wan Akmal Haikal bin Wan Ahmad. My student number is 2021460274, and I'm going to present about logical connectivities and negation. Next, we go to logical connectivities and negation. For all open statements, Px and Qx defined for pre-described universe, and the universally quantified statement known as conditional statement defined as for all x, Px implies Qx. The first logical connectivities is the conditional, which is it is the same as the statement given. Next, we have contrapositive, which is we have to exchange the position of implication, which is from the statement given, Px equal to A, Qx equal to B, and when we apply contrapositive logical connectivities, it will be B implies A, which is Qx implies Px, and we have to add the negation symbol in front of each statement. Next, the third one is converse, which is we have to only exchange the position of implication. And the last one is inverse, which is we have to only add the negation symbol in front of each statement. The following table shows the rule for negating statement with one quantifier. Number one, we have negation of for all x px, there are logically equivalent to there exists x, not px. Next, the negation there exists x px are logically equivalent to for all x, not px. And the third one, we have negation for all x, not px, that are logically equivalent to there exists x, not px. They are the same as there exists x px. And the last one is negation there exists x, not px, are logically equivalent to for all x, not px. And the final answer is for all x px only. For the better understanding, here is some example. Given the statement for all x px implies in bracket Rx or Qx, find the contrapositive, converse, and inverse for the given statement. Okay, the first one is contrapositive, which is I mentioned earlier. We have to exchange the position of the implication and apply the symbol of negation in front of the each statement. And then we solve it and got the final answer, which is for all x not in bracket not Rx and not Qx implies not Px. Next, we go to converse, which is the converse we have to only exchange the position of statement in the implication. Next, the last one is inverse, which is we have to only add the negation symbol of the statement in the implication, and we got the final answer for all x not px implies in bracket not rx and q not qx.
Next is nested quantifier. The definition nested quantifier is to negate a sequence of nested quantifier. You flip each quantifier in the sequence and then negate the predicate. For example, the statement is for all x, the axis y, pxy. So when we negation, we get the axis x for all y, pxy. Next is example 1. Let the universe of all integers and pxy denoted the open statement x plus y equal to 17. Consider the statement. The statement is for all x, the axis y, pxy. And the full statement is for every integer x, there exists an integer y such that x plus y equal to 17. This statement is true because when we select any x, the integer y equal to 17 minus x does exist and x plus y equal to 17. But we realize that each value of x gives rise to different value of y. Example 2. Determine the true value of each statement below according to the given. Justify your answer by giving examples or counter example. The first statement is for all x, bracket x square greater than 0. The universal set is set of all integers. The true value is false. And you get the counter example, x equal to 0. The second statement is for all y, bracket y cubed plus 2. The universal set is set of real number. The true value is false. And you get the counter example, and y equal to 0. Next is example 3. Let px equal to x square minus 8x plus 15 equal to 0. And qx, s is odd, and rs, s is greater than 0. The question is for the universe of all integers, determine the truth or falsity of the following statement, given an example or counter example. First statement, for all x, qx imply px. The true value is false, and you get the counter example when, for example, when x equal to 7 and qx is 7 is true, but when p7 is false. The second statement, the axis x, bracket px imply bracket qx and rs. The true value is true. You get example when x equal to 3.